Welcome back to ECE 320A. Homework number 8 is due today at 4, I believe, is the close of the drop box, or that's when it is due. Solutions should be available, I believe. I think I made that at 5, unless I forgot to do the AM, PM. Maybe it's already available, but I think it's available today at 5 p.m., the solutions. There is an exam review tonight. Is anyone planning to be there? Oh, okay, so there will be some attendees. I didn't know if anyone would be there or not, but that's going to be in the Harville building in room 102. I think that's where it was last time. So that's at 6 p.m. tonight for an exam review. And our exam, wow, is Thursday, isn't it? Guess I need to create an Maybe that's what we'll do at the exam review. You can help me cook up an exam. Now how many are attending? Today what I want to do is simply review the process for exam number 3, and that should be like the previous exams. And then we will get into Bode Plots. Exam number 3, now you have 3 sheets of notes. 6 sides to deal with. You may not need all of those. Maybe you can already collapse all of that down into 4 sides of a paper or of papers. Calculator and writing tools are available, but nothing else. No cell phones, no computers, no textbook, and no course notes. The topics are homeworks 6, 7, and 8. That's the material that will be on the exam. 3 kind of ideas are S-domain circuit analysis, which includes being able to get these S-domain impedances for RLs and Cs, put those into a circuit, draw the circuit, incorporate sources. That means you need to be able to Laplace transform anything. You also need to know how to incorporate initial conditions and find initial conditions. What are these limiting values that might establish initial conditions on inductor currents and capacitor voltages generally, and finding transfer functions. When you're finding transfer functions, what happens with initial conditions? You don't need to worry about those. So you don't have to incorporate initial conditions in your circuit if you are simply doing or finding the transfer function between an input and an output. Convolution, we'll talk more about that tonight in the review session, and you have a fair amount of material on D2L, but you need to know how to do convolution. Obviously, this sort of breaks down the exam contents. Convolution might represent a third of the exam, maybe. So you need to know convolution. It may represent more than that, actually, because I don't know if I'm going to make sinusoidal steady state analysis a third of the exam, but you need to know how to perform sinusoidal steady state analysis, finding h of j omega at omega naught analytically and graphically, but this does not then include Bode plots. Don't everybody leave. But we'll be talking about Bode plots today, which will be on the final. And your understanding of Bode plots will provide you with a way of actually sort of checking your work or understanding what you're doing more clearly, hopefully, on the exam. Are there questions about the process or what's happening today? Lecture, tonight, review, Thursday. Is today Tuesday? I'm so mixed up. Seems like we're on Friday. It's been that many days, but it's just been Monday and Tuesday, hasn't it? Half of Tuesday. Okay. On Thursday is your exam in here. Questions on that? and you should be able to find h of j omega naught analytically. By that I mean numerically, plugging in j6 or j100. Can you now find h of j omega naught, which is simply a complex number, a magnitude and an angle, and use that to determine sinusoidal steady state? I might ask you something more specific and say, okay, for your pole factor at with the pole at -10, what's the angle that it contributes at a frequency of 25 radians per second? And you should be able to give me that information. Just what is that single factor contributing in terms of an angle towards that overall transfer function? Is that making sense? If it's a pole factor, you know that it needs to be contributing a negative angle once you've found the angle, but you can then graphically sketch the picture associated with finding that pole's angular contribution to the overall h of j omega naught. Let's now look at Bode plots, which are actually a quick way of sketching h of j omega naught without having to compute all these omega naughts as you walk up the imaginary axis. Now you can sketch each of these individual terms and at the end add all of those up, and you will have your magnitude response as a function of frequency. Your magnitude plot is in dB. That allows you to add each of these terms, and your phase plot is in degrees as a function of frequency. What we are going to be looking at, you can sketch Bode plots for poles and zeros everywhere in the complex plane, but we are going to emphasize those that have all of their poles and zeros in the left half plane, and we can have poles and zeros on the imaginary axis, but we won't deal with non-minimum phase or zeros or unstable systems when we're sketching Bode plots. So I'm going to just say, and it simplifies these techniques. I'm going to say then that the techniques that we are going to be using or describing are for minimum phase. And since we are allowing poles and zeros on the imaginary axis, I'm going to say that techniques for minimum phase, let's say real factors. We also could have complex factors, but we're actually going to turn those into, in this class, just for simplification purposes, into two real poles. And we'll talk about how we do that. And so that is simply an approximation. Minimum phase for those factors says that all of the poles and zeros in those factors or of these linear factors are in the left half plane. If you needed to sketch something for right half plane poles and zeros, then I would recommend that you first sketch it in the S plane and sort of look at what's going on. The magnitude responses will be exactly the same. The angles are going to be different. Your angles from a pole at +2 is different than your angle at S equal to, or for a pole at S equal to -2. Let's go through this process of sketching a Bode plot using an example. And the example that we will use today is a transfer function capital H of S having a gain of 4,000 and a numerator factor of S plus 0.1. Then in the denominator we have an S plus 200, and an S plus 6 squared plus 8 squared. What form is that in? If I ask you what form that transfer function is written in? Could you tell me what form that's in? Pardon? Pole zero. You can see the pole factors and the zero factors explicitly. This is then in what we are calling our pole zero form, and that is not actually the form. This is the form you would want to sketch it in the S-plane for the graphical h of s or h of j omega. But for the Bode plots, we actually want it in time constant form. So we need to normalize these constant coefficients. 200, we actually want to make that equal to 1. The 6 squared plus 8 squared, which ends up being 64 plus 36, or 100, or 10 squared, we want to factor out that 10 squared and make it 1. Likewise, upstairs in the numerator, we want to factor out that 0.1 and make that constant 1. That makes it time constant form. But before we do that, sometimes it's nice to just know where everything is before you proceed any further. And to do that, let's just remind ourselves of what we have. A zero. Do we have any finite zeros? It's at minus 0.1 radians per second. That's the value of s that causes that numerator to vanish. That's a zero, and we only have one of those finite zeros, and this is coming from a linear zero factor because we had an s plus 0.1, and that exponent on the s was a 1, s to the 1. So that means it's linear. It's linear in s, if that helps or provides any more information. What about our poles? We have 1 at 0, which typically I will say, oh, we have a pole at the origin. Or we might have a 0 at the origin if we had an s by itself in the numerator. And those we treat differently than these linear factors. That's why I identified that first 0 as a linear factor. We have another pole at minus 200. And that is arising from a linear pole factor. Again, that was this s plus 200. And we have then this pair of poles that are complex conjugates. S equal minus 6 plus and minus J8 radians per second. And this I might call then a quadratic. And since it was downstairs, quadratic pole factor, because it came from an s squared expression. Now what we're going to do is we are actually going to parameterize that quadratic in a special way, or with a special structure, so that we can identify the natural frequency, omega sub n, and the damping ratio, which is now a new Greek symbol, this zeta symbol. And we'll make more sense of that as we introduce the factored form. But if we look at, so now let's look at this quadratic factor in a little bit more detail. I have s plus 6 squared plus 8 squared. That's s squared plus 12s plus it's a nice 3, 4, 5 triangle, so that's now really just 100 sitting out there as its constant. So I now have this quadratic, and we know by where it came from that has complex conjugate roots at minus 6 plus and minus J8. If we know we have complex roots, then we like to parameterize that as a quadratic that is s squared plus 2 zeta omega sub n s plus omega sub n squared. That's the factorization that we're going to use. So we need it to be monic. We need the leading coefficient of s squared to be 1. And then we write it as s squared plus 2 zeta omega sub n s plus omega sub n squared. This omega sub n, which is right here, and squared, is our natural frequency, which is different than the damped frequency. What was our damped frequency in this system? That was the omega sub d, which is how far up on the vertical axis we are. And where was that? If I said s is equal to minus 6 plus and minus j8, how far up vertically are we? 8. So the damped frequency is 8. The natural frequency is actually 10. And that's actually the distance that point is, minus 6 plus j8. That's the distance from the origin, is 10. And this zeta value is our damping ratio. And we can find those now for this specific set of complex poles. We can see that omega sub n squared, by comparing coefficients, is simply 100, or we now know that our natural frequency is 10 radians per second. And if we look at the linear coefficient, or the coefficient associated with s to the 1, we see that we have 12, and that should be equal to 2 zeta omega sub n. But that's just 6 is equal to zeta omega sub n, and we've just found what omega sub n is. So our damping ratio, which is going to just be between 0 and 1, that's its only values, that will be 6 divided by omega sub n, which is a value of 0.6 in this particular problem. So when we start talking about natural frequency, hopefully now you know where that's coming from. That's the distance you are away from the origin for those complex poles. And the damping ratio, that's between 0, which makes these roots purely imaginary, and 1, which makes them completely real when they're that far away from the origin. And we're going to be living on this arc from the origin that's of radius or distance omega sub n. Meaning, pictorially, I keep talking with my hands. In pictures, where were we? We were at minus 6 plus and minus j8 for our pole. But now I'm saying that this particular distance is actually our natural frequency. And our zeta value, the damping ratio, is proportional to that angle. This is more than you wanted to know, but zeta is now cosine of theta. Is that right? What did we just compute for zeta? That was 6 over 10, wasn't it? Which is what this says. The cosine of theta now says, oh, the adjacent side is 6 and the hypotenuse is 10. What we're going to do in this class is we're going to make the following, what you're going to think is a tremendous approximation, or a very large approximation, but we're going to say, you know what, for this class, we're not going to worry so much about the damping ratio. We're just going to swing that pole that's at J8 and this pole at minus J8. We're going to swing those around until they are completely real. And we're just going to sketch the Bode plot for those two real poles. The zeta just gives us more interesting shapes in the Bode plot, but we don't care so much for this class, those slightly different interesting shapes. We'll talk about that as we go through. But we're going to swing those down to where they become two real equal poles, or two real equal zeros, to sketch their Bode plots. So we need to learn how to do linear factors, poles and zeros at the origin, and constant factors to sketch those. Let's now first, before we get too far into this, let's convert that transfer function into time constant form. Or another way of thinking of this is you are actually normalizing the constant coefficient, or the constant coefficients, in linear and quadratic factors to 1. That's what we're doing when we put it into time constant form. In this particular case, we had h of s. First thing, we need to keep track of that 4,000. We can't drop that. But now in our numerator, we had s plus 0.1. We want to get rid of that 0.1 and actually make it 1. So we want to factor out a 0.1 from that numerator, but that means the s needs to be divided by that factor, and we have a 1 right there. So that now, if we think of whatever is scaling s is our time constant, this would be tau s. Tau is now 1 over 0.1, or tau is 10. So the time constant of that 0 is 10 seconds. And it's really close to the imaginary axis. All right, that's the first form or factor that we've normalized. S we don't need to mess with. That already was okay. But then the next one was S plus 200. We factor out the 200. And we have S over 200 plus 1. And then we need to factor out the omega sub n squared, which in this case was 100. And after you've done this a while, you learn that that's now s squared over 100, but that's just s over 10 quantity squared, plus 12 over 10 over s over 10. We want to keep that s over omega sub n in play, and then we have plus 1. That's what we factored out. So here is our quadratic factor. What I've done for that is the following. We think of that as s squared plus 2 zeta omega sub n s plus omega sub n squared in sort of its pole 0 structure. I've now factored out an omega sub n squared. So I have an s squared over omega sub n squared plus 2 zeta omega sub n s, omega sub n squared I'll write as omega sub n times omega sub n, plus omega sub n squared over omega sub n squared. But that's now I can cancel one of these omega sub n's, leaving me with 2 zeta S over omega sub n plus 1. And that's really what I've written down right there. Remember, zeta was 6 over 10, and that 12 over 10 represents 2 zeta. All right, now we're ready. Now that it's in time constant form, we have the following strategy for sketching these Bode plots. First, we sketch the individual terms. That means we sketch the linear factors, we sketch the quadratic factors, we sketch the poles and zeros at the origin, and we sketch the constants. And after we've sketched all of those individual pieces, we simply look at those sketches and we add them up, point by point, meaning omega by omega, frequency by frequency. So now we add all of these terms up for all frequencies. That's the strategy. Now let's look at sketching these individual terms. Or the different types of factors. First one that we can identify is the constant term, or the constant factor. And that's now not 4,000, it's 4,000 with all of these other pieces that have been pulled out. Our constant factor now not only has 4,000, but it now has that piece, this 200, and that 100 all combined to give us our constant in time constant form. So that's why we need to convert it to time constant form so that that guy won't change as we adjust frequency. We now have for the magnitude, because we have two different things we're sketching, magnitude and angle, or magnitude and phase for each term. For the magnitude, we had the 4,000 times 0.1 over 200 and 100. And if I divide 200 into 4,000, I now have 20. Is that okay? So now I have 2 over 100. And I can write that many different ways, 0.02, or I actually may write it when I'm finding the magnitude as 2 times 10 to the minus 10, because I'm going to be using the log to compute these. So if I now find the dB value of that gain, it's at 0.02. That's a pretty small value in terms of the gain. But now I'm looking at 20 times the log of 0.02. But to get a feel for that, I could write that as 20 times the log of 2 times 10 to the minus 10. Because I think we've already figured out what the log of 2 was. Now we have, this is 2 times 10 to the minus 2. This is now the product of 20 times the log of 2. Oh, let me go ahead and factor out that 20 plus log of 10 to the minus 2. And that minus 2 can be pulled out in front, since this can also be written as minus 2 times the log of 10, giving me now 20. Do you remember what the log of 2 was? 0.3, wasn't it? Because we needed 3 dB down when we were square root of 2. If you don't remember, you'll start to remember all of these things, maybe, and then you can help me remember, okay? Then we have minus 2 times the log of 10. What's the log of 10? Base 10, log of 10, 1. So this is now minus 2. This is now 20 times minus 1.7. Or this is now minus 34 dB for all frequencies. And that's now the magnitude plot due to the constant term of 0.02. If we wanted to sketch that, let's say here is our 0 dB line, and maybe this is a frequency of 10 to the minus 1, 10 to the 0, 10 to the 1, 10 to the 2, and we usually just label that as omega. Now I'm down below minus 20 and minus 40, or in between there, and now I'm looking at minus 34 dB. That's the Bode plot of that constant term for all frequencies. That contributes a value of minus 34 dB at all frequencies. That's all that's saying. What's the phase of this gain term look like? If I needed to sketch the phase of this gain, it's 0, isn't it? Because K was positive. So our angle, or the phase of that constant, is 0 degrees for all omega, and I'm not even going to bother sketching that. That would just be the axis without anything on it. Let's now look at some of these linear factors. I'll call this one 2a and say this is our 0. Our 0 was this factor s over 0.1 plus 1, which we are trying to sketch this as we're walking up the imaginary axis. So the s now becomes j omega, and we're now trying to sketch this factor j omega over 0.1 plus 1 for all frequencies, both its magnitude and its angle or phase. So now let's look at the magnitude of this particular factor. And again, if you forget, just open up your fairy tale book and think Goldilocks, right? That's what we're doing. We're looking at small frequencies, large frequencies, and that sweet spot. The sweet spot being right at the pole or 0, right at the break. And small means what relative to the break frequency? 1/10 or a decade below. Large means big, or 10 times the break frequency, a decade beyond. So let's apply that to see if we can understand what the magnitude's going to look like. Now we have 20 times the log of the magnitude of j omega, 0.1 plus 1. For small values of omega, what's that argument of the logarithm going to approximately be valued at for small omega? If I set omega equal to 0, extremely small, what's the argument of the log? 1. So now I have log of 1. That's 0 dB, isn't it? So this factor is saying that I'm actually flat. For small frequencies, it's at 0 dB. Until omega equals, we're going to say, until it gets all the way to the break frequency. And that's when we start worrying about its change with omega. So we not only went from really small, which was 0.1 omega, but we went all the way up to omega, and then we'll intersect that with what was really happening at high frequencies of omega. It now breaks, or has a change in slope at that break frequency, which is occurring when omega is at such a value that the imaginary part is equal to the real part, The real part is 1, so we're just looking at when does omega equal its denominator, or whatever it's being scaled by. So we want to make omega over 0.11, and that's when omega is 0.1. Once it breaks, what's the slope? If I said, what is this doing, this whole term, 20 log of that argument for big values of omega? Now omega becomes such a number that it's 10 times 0.1. So now it's J10 plus 1 and bigger. J20 plus 1, J30 plus 1. What's happening as we adjust omega? We have 20 log of omega, don't we? And log of omega is what our independent variable was plotted with respect to, so it's now changing at a slope of 20x log of omega. This is a zero factor, which is upstairs in our transfer function, and so our slope change is now positive. It's plus 20 dB per decade after that break. So we now have a slope of plus 20 dB per decade. And that's sort of a verbal description of what that zero factor is doing. And if you wanted to get finer in your resolution, then you might talk about something other than a decade. But a decade is a factor of 10, and that produces then this 20 dB per decade. If I went up an octave, that's a factor of 2, isn't it? And that corresponds to 6 dB per octave. That's the same slope, it's just over a different expanse of frequency, either a factor of 2 or a factor of 10. So in this particular factor, if I said in our straight line approximation, what is the magnitude of our, or what's the value of our magnitude at 0.4 radians per second? What's the break frequency? 0.1. A decade above that would put us at what frequency? Omega equal to 10 times 0.1, so at 1. And then we would be 20 dB above where we were starting. But now I said, wait a minute, I asked somewhere between 0 and 1. So I know I'm between 0 and 20 dB, but now I said 0.4. So you go from 0.1 to 0.2, what's that interval or factor? 2, that's an octave. From 0.2 to 0.4, factor 2, another octave. So we have 2 octaves between where we started. We started at 0 dB, we go up 2 octaves, and how far are we going per octave? 6. So how far am I up? 12. And that's between 0 and 20. So now we know that our magnitude, due to that particular factor, should be contributing 12 dB at omega equal to 0.4. Is that making sense? All right, so now if we sketch that, if we now said here is the magnitude of our linear zero factor, here is 0 dB, and now we had, what did I have? Did I have, oh, let me do this differently. 10 to the minus 2, 10 to the minus 1, 10 to the 0, 10 to the 1, 10 to the 2. I'm not going to get up that far. But now I said that my plot was flat at 0 dB until I reached my break. And once I hit the break, then I start sloping, and since it's the numerator, it's a zero factor, I'm going up with my slope. I now would be at 20 dB. A decade beyond that, I would be at 2 times 20, or 40 dB. 2 beyond that, so this is now my magnitude plot. And that just keeps going, where this slope is plus 20 dB per decade. Is that clear, how you would sketch that linear factor, that linear zero factor's magnitude plot as a function of frequency? What's the phase of that linear factor going to look like? And here's where Goldilocks becomes even more prominent. Because now what we do is we actually look at those three frequencies, find the angle at those three, and then just straight line connect those three dots. To find the phase for these linear factors, we're simply going to look at three frequencies, and now you know what those frequencies are going to be. In fact, we're going to be flat, then we're going to slope, and then we're going to go flat again. So the first frequency of interest is the baby bear, omega 1. And that's a decade below the break. That's this 0.1 factor. This is now a decade below. Does the book say cutoff? Maybe I should say cutoff frequency. In this particular example, we know what omega naught was. This says that we're going to be flat at 0 degrees until we reach a decade before the break. And that's at 0.01, or 10 to the minus 2. And at this particular frequency, our angle is 0 degrees. Because if you look at this factor, which is, the factor is now this j omega over 0.1 plus 1. Now we have j 0.01 divided by 0.1 plus 1. We now have 1 plus j 0.1. That's not very much in the vertical direction, is it? So we're just assuming that's 0 degrees still. Now the second one, frequency, is our sweet spot, which we'll just say is omega naught. And at that point, in this particular case, when I set omega naught equal to 0.1, how do my real part and imaginary part relate in that factor? I have 1 plus j1, don't I? What's the angle of 1 plus j? 45 degrees. And since it's a numerator factor, it's a positive angle. This now says that the angle there is exactly 45 degrees, right at the break. If you evaluated the angle of this expression at omega naught, that's going to be 45 degrees. And since it's upstairs a numerator, that gives us the 45 plus. Then the other angle, omega sub 2, is a decade beyond the break. So that says 10 times omega naught, which in this particular factor is simply 1. And at that point, our theta, now we have 1 plus j10, and that's a very big angle, and we're just going to approximate that by the extreme that that linear factor can produce, which is 90 degrees. This is now a decade beyond or above the break. Now we're in a position to sketch the phase. I said we were at 0 degrees at 10 to the minus 1, and we're actually at 0 before that. We are at 90 degrees at 1, which is 10 to the 0, and for all frequencies thereafter. And then I just connect these 2 points with a straight line, which says that I need to be going through 45 degrees right there. And if I needed to think about it, I'm now sloping at plus 45 degrees per decade. So I need a 90-degree change over 2 decades. And that's now my, so this value here is plus 90 degrees. Are there questions on that? This is 0.1 times omega naught for this omega naught. This is omega naught, and this is 10 times omega naught in frequencies. And what we're doing with this phase, you can sort of illustrate with a S-domain sketch. If we now were here with our 0 at some omega naught, then this might be 0.1 omega naught. This would be j omega naught. And way up here would be 10 j omega naught, or j 10 omega naught. Maybe I should rewrite that. And we're interested in the angle. At those positions. When we're at a value omega naught a decade below or less, it's not a very big angle. So we're just approximating that to be 0. Then we say, oh, right at the break, well, that's an angle of 45 degrees for a single linear factor. And if we go 10 omega naughts, that's way up on the imaginary axis. And so we are, the biggest angle we could ever get would be 90 degrees. And we're just going to go ahead and say that's fine. We'll call that 90 degrees. And we just connect those with straight lines. That's what we're doing. Let's look at the second linear factor. If my computer, well, I'm just going to keep it the same, I guess. 2b. To be or not to be. Might as well do some Shakespeare. Oh, what? Oh, yeah, I read an editorial that I wasn't. Yeah, I better be quiet. Okay. It was slamming engineering, sort of. It was talking about the humanities. And it said something like, well, you're never going to get a guy, what was it? This was written by a lady, so don't take offense at this. What was it? Something like you can't propose to, or you can't communicate romantically via equations. You need like a poem or something. You need something more directed towards the humanities. And I thought, what about our sine squared plus cosine squared? I think never mind. All right. Let's get back to factors. Here we have our pole factor, our linear pole factor, s over 200 plus 1, written in time constant form. Now we replace the s with j omega, and now we have to sketch the magnitude and phase associated with that factor. But remember, it's a pole factor, so now everything is down in this basement. Things are going to go down, negative. What would we do for this one? Can we just sketch it now, the magnitude, without going through all the, let's say this is 10 to the minus 1, and you would line all of these up. All these pieces would be on the same plot. I'm just doing it in different pieces so that I don't have to keep scrolling up and down. But what does this one look like? First thing that we need to do is identify our break frequency on the log scale, right? We're 200, which is between 100 and 1,000, right? But how far in between? What's the log of 200? What's the log of 2? 0.3. So it's 30% of the distance between 200 or 100 and 1,000. So if we went over here and said, oh, this looks about like a third of the way, this is now our break frequency, 200. Is that making sense? We're now 0 dB out to that break. And then what happens? Now it goes down because it's a pole factor and it's going down at 20. So what I would do is I would go over here to 2,000 and I would say, oh, you know what? I need to be down at minus 20 dB at that point. And then I just get my ruler out and I sketch that and I just connect the dots. And you thought you were beyond connecting dots. This slope then is minus 20 dB per decade. What's the phase going to look like? Are there questions on the magnitude plot? Now I'm really messing things up. These all should be aligned, but they're not in my sketch. What are my 3 points of interest? What's the first one maybe that you'll write down? 20. So that's a third of the distance between 10 and 100. So if I call that 20, then I'm going to be right there's my sweet spot of 200, and then here's 2,000. And those are my 3 frequencies of interest. I'm going to be 0 degrees until a decade before the break. After a decade beyond the break, I'm going to be contributing an angle of 90 degrees, but since I'm downstairs in the basement, that's minus 90 degrees. And now I simply connect those limiting values of 0 and minus 90 degrees. This is now minus 90 degrees. This point, if I needed to find it, would be exactly minus 45 degrees. And that's my phase due to the linear pole factor at 200. Questions on that? So now you know how to do constants, you know how to do linear factors. Let's look at what happens when we have things at the origin. In this particular example, we had a pole, didn't we? That gives us this expression S. That's its factor. We replace S with j omega. Now we're just playing with j omega. And we want to sketch its magnitude and phase as a function of frequency. If we look at the magnitude of this, in dB, we have 20 times the log of the magnitude of j omega. What's the magnitude of j? And if you forget, just go over here and on a piece of paper say, you know what, he's not going to fool me. Here is j, isn't it? That's j. What's the length from the origin to j? 1. So the magnitude of j is 1. I can now say that this is the same as 20 times the log of the magnitude of omega. The j doesn't impact the magnitude. I only had that imaginary part, didn't I? If it was real plus imaginary, I need to keep those two orthogonal directions clear. But now what is that going to do? Do you remember what we had before in the linear factor? We had this 20 log of omega plus another term. This one never breaks, does it? This one's always sloping. This always slopes for all frequencies omega. It always is sloping, or it never breaks. So in this case, we do not have this additional piece. That we would have in a typical linear factor. Now, if I'm at a birthday party and I'm pinning, now I know the slope. I know the slope, and where was this factor located? Upstairs or downstairs? Was it a 0 or a pole? This was a pole at the origin, so I now know I have a slope of minus 20 dB per decade, always. Now I just need to walk up and plop that somewhere on my Bode plot. Where do I put it? I know it's just this line that's always sloping. Now what we can do is we can just pick a convenient value of omega and say, oh, I can locate that guy, that sloping line. So the question that I'm trying to get us to think about is the following. Where do we place this line that's always sloping? Where do we locate this sloping line? And I actually don't want to finish that question. Let me convenient point might be omega equal to 1, wouldn't it? Because we know what the log of 1 is. That's 0, isn't it? So we know at omega equal to 1 that we have a value for this sloping line of 0 dB. What that means then is we have this pole at the origin is always sloping with a slope of minus, since it's a pole, 20 dB per decade. It was just one pole at the origin, so it's just minus 20. If it was two poles at the origin, it would be twice that. It would be sloping at minus 40 dB per decade. We know it has this slope always, and now we know where it actually passes. And passes through 0 dB right at omega equal to 1 radian per second. Now we can sketch this pole at the origin. We're keying off of what's happening right there at 1 due to this term contributed by this pole at the origin. This is now 0 dB. We know that that sloping line needs to pass right through there. At omega equal to 1, it's at 0. And now because it's a pole, it has a negative slope, which means a decade beyond 1, which is 10, we better be at minus 20. A decade before 1, which is 0.1, and it's always sloping with a negative slope, it better be up, plus 20. So here is plus 20 dB. Here's minus 20 dB. And if I had drawn this accurately, that sloping line never stops. And what's that pole at the origin do to our gain at DC? What's that pole at the origin going to do to our magnitude at low frequencies? How big is that gain going to be in that system? Now if I somehow put on my spiked shoes and I could walk up that 20 dB slope, how high up would I go at low frequencies? I'd just keep walking, wouldn't I? I'm beyond 60 dB. I'm beyond 100 dB. That's huge, isn't it? So I have infinite gain at DC when I have a pole at the origin. That's what that's saying. That may or may not be a good thing. A lot of times that's a good thing because that really, in a control system, that really drives your error to 0 if you're trying to make something happen accurately. So you have a really large gain at DC, and does that make sense? If you had H of S with an S in the basement, and you let S go to 0, what happens to the magnitude of that transfer function? It blows up, doesn't it? So this picture should be consistent with what you would think it should be doing. Now, what's the phase of this? Pole at the origin. Here's 0 degrees. Here's 10 to the 0. Boy, I'm really messing with these left and right shifts on these frequencies. You would keep all of these in the same vertical direction. Your omega equal to 1 would always be lined up, and then you could start adding all of these terms together. Now I'm looking for the phase or the angle of 1 over j omega. That's what I want to sketch as a function of omega, the angle of that. But this, if you don't see it right away, you go, well, that's just a ratio of two numbers. So that means I take the angle in the numerator and subtract the angle in the denominator. So I now have the angle of 1 minus the angle of j omega. What's the angle of 1? So now you're over here in the S-plane, and somebody says, here's 1, and now what's the angle to get me to that point? 0. So now this is 0 degrees. Now I'm also here, or I'm here for any value of omega. I'm on this imaginary axis, and now I'm going to that point. I'm going to that point. I'm going to that point. What's the angle for any omega? 90 degrees, isn't it? So this is 0 minus 90. So this is minus 90 degrees for all omega. This is an easy thing to sketch. It's flat at minus 90 degrees for all. Did I draw my, oh, I did. So now I have this. That's my phase plot for my single pole at the origin. Questions on that? Now we get to the fun stuff. Really? I was so excited before. Yes, sir. So now the question was, if we have two poles at the origin, I think, if you now had 1 over s squared, now your magnitude factor is going to be doing this, isn't it? It's going to cross the same 0 dB at 1, but now its slope is minus 40 dB per decade. And it keeps increasing at that slope. Is that okay? And the angle, or the phase of 1 over s squared, is just twice what we just sketched. It's now not 90. It's 2 times 90, or now we're down at minus 180 for all frequencies. That's what you would do for a doubling of the pole at the origin, if you had two poles at the origin. A double integrator, which is a pure mass system, if you wanted to think mechanically in dynamics. All right, so let's introduce some damping in that dynamical system, which gives us a quadratic factor. Good segue, huh? So now instead of having just an s squared, now we have an s squared plus alpha s plus beta, a quadratic factor. Or we may call this just a complex factor. And to get us remembering what we were referring to, here is the top pole in our diagram. We have its twin or cousin downstairs at minus J8. But this is now where our pole was located. And what I had suggested we were going to do is we were going to just take our string. We carry a piece of string with us all the time so that we can sketch. We're going to take our string, tie it around our pencil, take the other end and put it on the origin, and now just draw an arc of radius 10, which is our natural frequency here. And if we do that, this distance would now intersect here at J10, and this would be at minus 10. And the values of zeta, this would be no damping. Remember, we're just sitting there oscillating. If we had a pole at J10 and it never dies, we have no e to the minus piece to that. Down here, we would be critically damped, right at the real line. We would have two poles at minus 10. That wasn't a very, my string was kind of rubber band, elastic, had some elastic in it. Didn't stay taut, did it? I thought it looked pretty good over here until I got to looking at the projection. That's not a real good quarter circle, is it? But it's supposed to be. So that's a radius of 10. What we are going to do, even though we may have a value of zeta of 0.6, which is what this was, we're going to make that zeta 0.1 just so we can sketch it. So what we're doing is we are saying that instead of having this factor that looked like, what was it, s over 10 squared plus 2 times 0.6 s over 10 plus 1. What we're going to do is we are going to agree in this class, we're always going to just approximate that to be 1. That zeta value, this was our zeta value. Don't say that this is what the Bode plot actually does. Just say this is that crazy Tharp's way of approximating things. It just makes your job easier. That's why I'm doing it. But if we now let zeta equal 1, we now have s over 10 squared plus 2 s over 10 plus 1. But that's a perfect square, isn't it? This is now s over 10 plus 1 quantity squared. And now we just have to sketch two factors that are at the same frequency of 10. And these are real factors now. We've slid that with zeta equal to 1 all the way down. So now what we've done is the approximation has swung that pole from the upper half down to minus 10. It's going to swing the one from the lower half up to minus 10, and we're going to have two real poles at minus 10. Now, how do you think we sketch that? Now we just double everything, don't we? If we now looked at what we have for this particular case, our magnitude what do we sketch? I'll do the easy part. It's 0 dB until where? For this particular factor. Till we reach 10, right? The imaginary part is going to equal the real part. Then what happens? Now we're not at minus 20, we're actually at minus 40 because we're twice what we were before, a decade later. So that now, here we're at minus 80. And that just keeps sloping. This is now minus 40 dB per decade. Does that make sense? What about the phase? What's our starting value of phase? So for small omega, this looks like a real number, doesn't it? The angle of a real number, 0 degrees. And then when do we need to start worrying about when this is going to be moving away from 0? This is baby bear, isn't it? This is a decade before the break. The break was at 10, so now right at 1 is where we start to transition. A decade beyond that break, what are we going to finally end up with in terms of phase contribution? We now have poles, so it's got to be negative, and we have 2, and each pole gives us minus 90. So now we have 2 times minus 90. We're minus 180. A decade beyond the break. And now we simply connect these dots. And this is minus 90 degrees. Now what do we do? Now we add all of those pieces together. That's why we learned how to add up waveforms in the time domain. Now this is similar. It's just now our independent variable is frequency. But when we start going up at 20 dB per decade and then we start going down at 20 dB per decade, we'll just be flat as a magnitude. If we're going up 20 and down 40, now we're effectively down 20 dB per decade. So you just work your way from small frequencies to higher frequencies and keep track of first where you started, which in this case was going to be minus 34 plus this sloping line. That's our starting point, and then we move on from there for the magnitude. And the angles are similar. Yes? On this one, we are going down at minus 40 dB per decade because effectively now we've approximated this quadratic to be 2 linear poles. And each pole factor gives us minus 20. We have 2 of those, so that's our minus 40 per decade. We'll pick up at that point in a week, right before Thanksgiving. See you Thursday, if not tonight.